Welcome to our lesson on mathematical logic. We'll be exploring the foundations of logical reasoning, which forms the basis of all mathematical thinking. Let's start with propositions. A proposition is a declarative statement that is either true or false. For example, Paris is the capital of France is true, while 2 plus 2 equals 5 is false. Expressions like x plus 1 equals 10 are not propositions because their truth value depends on x. Questions like, is it raining, are also not propositions. Logical operators connect propositions to form more complex statements. The negation operator, not, flips the truth value of a proposition. The conjunction operator, and, is true only when both propositions are true. The disjunction operator, or, is true when at least one proposition is true. The implication operator forms if-then statements. An equivalence, or if and only if, is true when both propositions have the same truth value. Truth tables help us systematically determine when compound propositions are true or false. For and, the result is true only when both inputs are true. For or, the result is true when at least one input is true. The not operator simply flips truth values. The implication operator P implies Q is only false in one case, when P is true and Q is false. This can be counterintuitive, especially when P is false. The equivalence operator is true when both propositions have the same truth value, either both true or both false. De Morgan's laws are fundamental principles in logic. The first law states that the negation of a conjunction is equivalent to the disjunction of the negations. The second law states that the negation of a disjunction is equivalent to the conjunction of the negations. In natural language, saying, it is not both sunny and warm, is logically equivalent to saying, it is not sunny or it is not warm. Logical equivalences are statements that have the same truth value in all cases. The idempotent laws show that repeating a proposition with and or doesn't change it. The commutative laws state that order doesn't matter in and or operations. The associative laws show that grouping doesn't matter. One particularly important equivalence is that P implies Q is equivalent to not P or Q, which explains why implication is true whenever P is false. Quantifiers allow us to make statements about collections of objects. The universal quantifier, symbolized by for all, indicates that a property holds for every element in a set. The existential quantifier, symbolized by there exists, indicates that a property holds for at least one element in a set. When negating quantifiers, the universal and existential quantifiers transform into each other. The negation of for all x px becomes there exists an x such that not px. Similarly, the negation of there exists an x such that px becomes for all x not px. These negation rules are crucial for constructing logical arguments. In mathematics, we use various proof techniques. A direct proof starts with a hypothesis and uses logical steps to reach the conclusion. Proof by contraposition exploits the fact that P implies Q is logically equivalent to not Q implies not P. Instead of proving the original implication, we prove the contrapositive, which is often easier. Proof by contradiction is a powerful technique where we assume the opposite of what we want to prove, then show this leads to a logical contradiction. A classic example is proving that the square root of 2 is irrational. We assume it's rational, express it as a fraction in lowest terms, and show this leads to both numerator and denominator being even, contradicting our assumption that they have no common factors. Mathematical induction is a method of proof used to establish that a statement is true for all positive integers. The proof consists of two steps: the base case, where we verify the statement for the smallest value, and the inductive step, where we show that if the statement holds for some k, it also holds for k plus 1. A classic example is proving the formula for the sum of the first n positive integers. Let's prove the sum formula by induction. For the base case n equals 1, both sides equal 1, so the formula holds. For the inductive step, we assume the formula is true for some k. Adding k plus 1 to both sides and simplifying, we get exactly the formula for k plus 1. By the principle of induction, the formula is true for all positive integers. Set operations allow us to combine and manipulate sets. The union of sets A and B, denoted A union B, contains all elements that are in either set A or set B, or both. The intersection, denoted A intersect B, contains only the elements that are in both set A and set B. The complement of a set A, denoted A prime, consists of all elements in the universal set that are not in A. Just like in logic, set theory has its own version of De Morgan's laws and distributive properties. These laws are crucial for manipulating and simplifying set expressions. Functions can be classified based on how they map elements from the domain to the codomain. An injective or one-to-one function maps each element in the domain to a distinct element in the codomain. This means no two inputs map to the same output. A surjective or onto function maps the domain onto the entire codomain. This means every element in the codomain has at least one preimage in the domain. In other words, the function's range equals its codomain. A bijective function is both injective and surjective. It creates a perfect one-to-one correspondence between the domain and codomain, where each element in the domain maps to exactly one element in the codomain, and every element in the codomain has exactly one preimage in the domain. To summarize our exploration of mathematical logic, we've covered propositions and logical operators, truth tables, De Morgan's laws, quantifiers and their negations, various proof techniques, set operations, and function types. These concepts form the foundation of mathematical reasoning and are essential tools for clear and precise logical thinking.